There are 6 samples in 2 groups. Each group has triplicates. The CH1 raw signal holds count values. Let's start with no processing. The distributions of counts depend on the number of total mapped reads. More total reads shift the histogram to rightward. RNA Seq datasets usually have variations in the number of total mapped reads by 2 times, sometimes more. Let's start with the preset scenario of the Subio platform, named RNA Seq count, and adjust steps one by one. If you click on a block, you can check how the block changes the data in the left histogram. Clicking on the triangle opens the option setting panel. In this case, the right peak is slightly right from the 75th percentile line. So we set 80. But you can put any between 75 to 90 in this case. Because you align the right peaks, the minimums become uneven. So, trim the left ends by the low signal cutoff block. The question is, what is the good value for the low limit? If you look at the scatter plot in the upper panel, the dots spread widely in the count range of less than 20 or 30. You can assign other samples and find that the noise signal boundary lies around 20 to 30. If you set the low limit at 30, imputation by 4.5 is suitable. 2 to the power of 4.5 equals 22.6, lower than the low limit set above but not too small. If you set the low limit at 20, imputation with 2 to the power of 4 equals 16, works fine. The last block turns expression levels into ratios against the average of the BJFF group. Click the Do Normalize button to finish. It overwrites processed signals. Let the scatter plot display the processed signals on the vertical axis. The vertical axis represents the average log2 ratios of NF6.1, BJFF. Line graph shows lines connecting 0 in the BJFF group and relative gene expression levels in the NF6.1 group. Let's see what happens if you don't have the cutoff block. Without the cutoff, you will get more differentially expressed genes in the low count range. Please note that restoring the cutoff clears many DEGs in the low count area. Next, we will see the case of TPM in the CH1 raw signal. In this series, you can view or compare TPM in the CH1 raw signals and counts in the CH1 reserve. Samples in this data set have around 50 M mapped reads, and the average length of coding genes is around 2K. The TPM here will likely be about 1/100th of the count values. Lowly expressed, very long genes have very small TPM values. Looking at the scatter plot of count values, you see the noise range at low counts. Pick roughly genes in the noise range and separate them from other genes with the Venn diagram tool. You can save them as measurement lists respectively. Back to the scatter plot of TPMs and compare the range of noise and signal genes. Most noise genes range TPM from 0.03 to 2. And the low limit of signal genes lies around 0.2. Please note that the TPM range between 0.2 and 2 is an inseparable mixture of noise and signals. Load the normalization scenario, RNA Seq, TPM, FPKM, RPKM, and adjust each step for this TPM data. Though the TPM is theoretically already normalized, it is safe to apply the global normalization. The 75th percentile line is at the peak of right, so set 75 for this block. As we saw, the noise signal boundary vaguely lies between 0.2 and 2. So we set 0.2. Turn the TPM to ratio at the last block. Click on the Do Normalize button to overwrite the processed signals. Assign the processed signals to the vertical axis of the scatter plot and see how the pre-processing worked. As you expect, you see many noise genes at the TPM range between 0.2 and 2. Let's see what happens if you don't set the low cutoff. There are a lot of genes widely spread in the area TPM less than 1. Next, let's see what happens if you set the low cutoff at higher than 0.2. You see that giving a higher low cutoff makes less noise genes appear. Because the boundary of noise and signal TPM is vague, you have to choose the strategy of accepting noise and remaining more genes for analysis or giving up many genes to reduce noise. Lastly, we see the effect of the Fill Missing Values block. Select the Average dataset and open the Datasheet tab. Please notice that there are no log2 ratios if one of the TPMs in BJFF or NF6.1 is blank. Putting the Fill Missing Values block before the Making Ratio block avoids such a problem. Because the former low cutoff is set as 0.2, give -2.5 to fill all blanks with 0.177. Click on the Do Normalize button to overwrite processed signals. Let's see the new processed signals in the Datasheet tab. Giving the suitable value to blanks makes the log2 ratio calculatable.